When an ionic compound dissociates in water, it forms an electrolyte which is capable of conducting an electric current. This is because the ions are free to move through the solution. In this example, we have sodium chloride as our ionic compound. You note we're getting two ions out of this, the sodium ion and the chloride ion. Because both of these ions get completely surrounded by water molecules when they're pulled out of the crystal lattice, completely surrounded by water molecules and able to move throughout the solution. Remember, the solution is mostly water anyway. Because they can move throughout the solution, we can have a flow of charges, which is a flow of current. Water itself is actually a very poor conductor of electricity. However, at high voltages it does conduct to a certain extent. This is because some of the neutral water molecules actually dissociate into two ions, the hydrogen ion and the hydroxide ion. This is a reversible reaction. This double-headed arrow here, this double-headed harpoon arrow, shows that the reaction actually proceeds in both directions. The water splits up into the two ions, but then those two ions come together and form the water molecule again. So the reaction proceeds in both directions. This is actually a better representation of what's going on. If you just had one water molecule, you get a hydroxide ion and a hydrogen ion. But a hydrogen ion is just a proton, very tiny, with an entire positive charge to it by itself. It doesn't stay by itself because it's highly reactive, so it hooks up with another water molecule and gives H3O+, the hydronium ion. You will actually never have any hydrogen ions in solution. You will always have hydronium ions. Under normal conditions, only about 1 of every 10 million water molecules actually splits up like this. The reaction is heavily biased towards the formation of H2O liquid. However, the reaction does involve ions, as did the dissociation of the sodium chloride we looked at first. Many chemical reactions involving ions are actually best represented by ionic equations, which we'll look at now. There are actually 3 parts to writing ionic equations. Let's look at this example. Solid sodium carbonate reacts with dilute hydrochloric acid. Carbon dioxide is a product. Another product is sodium chloride in solution in water. We can easily write an equation for this reaction like this. Here's the reaction equation for this example. The question told us that the sodium carbonate was a solid. It said that we're forming CO2 gas. It said that we're producing water as well, and that the sodium chloride formed was in a solution, so that's aqueous. Acids come also as aqueous solution. This is the molecular equation, sometimes called the formula equation. But there are 2 things to consider with what we have here. Firstly, acids, strong acids, as in the case of HCl, completely dissociate. So actually we're not going to have any HCl molecules. That will be dissociated into the hydrogen ions and chloride ions. Also, we know that one easy way to break apart an ionic lattice is to drop it into water. So this sodium chloride is very soluble in water, and that will actually also exist as sodium ions and chloride ions rather than the ionic lattice of sodium chloride. So in the case of ionic equations, any aqueous species we split up into the ions that would be present instead. This brings us to the second part. This is the full ionic equation. Any solid, any gas, or any liquid species are left alone. But any aqueous species get split into their ions. So in this case we've split up the hydrochloric acid, the HCl, into hydrogen ions and chloride ions. Also the sodium chloride has been split into sodium ions and chloride ions. You'll note the solid sodium carbonate, the liquid water, and the gaseous CO2, they get left as they were. But any aqueous species we split into the ions. because everything is listed, it's the full ionic equation. However, you'll note at the start, we have 2 chloride ions. At the end, we also have 2 chloride ions. The chloride ions haven't changed in any way. They're just sort of hanging out in the beaker, but not really involved in the reaction itself. In this example, the chloride ions are called spectator ions. Spectator ions are not actually not involved in the reaction process. They can actually be left out because they didn't really do anything anyway. Which brings us to the third part. This final one is the net ionic equation. Spectator ions are simply left out. Only chemical species which are actually involved in the reaction, which change in some way, are listed. The 2 chloride ions didn't do anything. They were there at the start, they were still there at the end, so they're spectator ions and we simply leave them out. So for ionic equations, we have the molecular equation, the full ionic equation, and finally the net ionic equation.
Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.